Hello students. In this video and maybe one or two more videos, I will do a review of the concept of functions and concepts related to functions around that you typically study either in a college algebra course or in a pre-calculus course. I highly recommend this video or any such similar content from any other creator to students who are starting on a intermediate level mathematics course either in a college or in a undergraduate institution. At some point, if you are taking a very advanced mathematics class, you probably should already be knowing everything here and you should not be needing to watch this video. But if you have just cleared your high school graduation and you are taking some class in mathematics other than college algebra or pre-calculus, or you have taken those courses earlier and are now taking a second level, the intermediate level mathematics course. um, these ideas, functions are at the center of many studies, many areas of mathematics, and a review, a brush up of those concepts will be essential to you. And I call this uh, review that I'm going to do a marathon review. Okay, which means we are not going to do a course in college algebra or pre-calculus, but we are going to talk about concepts at a fast pace. Okay, what you should do, you should be paying attention very closely as you watch and listen, and be ready with your notebook to take notes. Okay, here and there, I'm not saying everything you write down. Here and there, whenever you remember something that you have studied before and now you are listening to this video and watching, and it strikes to you, or sometimes you understand it in a better way, write it down. Okay, and do that whenever it feels that to you that this is an important idea that it came across to you in your mind. Okay, you will be your own judge, but because that instinct, your intuition will work, trust yourself. But do not watch passively, take notes. Okay, let me begin. The first topic is four ways to represent a function. Okay, that is the title, but in the process we will talk about what a function is and then talk about representing functions. A function is a rule that assigns to every input a unique output. Okay, that is the definition of a function. Two words are every and unique, very important. So you cannot take an input value and give it two different outputs, then it is not a function. Okay, and you cannot miss any input value. You have to assign an output to every input value. That is a function. Basic idea. When do and how do functions arise in real world, in nature? Whenever there are two quantities and one depends on the other, right? And here are going to be some examples. You know the area of the circle formula, pi r square, right? Now if you know the radius, then you can compute the area based on the radius. So we say the area depends on the radius, right? So area is now a function of the radius. And we often write that as A equals A of R. Area is a function of R. A of R. That is how it is read, and that is the interpretation. It is not A times R. It's not multiplication. Okay. But because sometimes we use parentheses for multiplication and students tend to get confused, you have to be clear in the context. You should know the context. Okay. Like that. And in terms of the various ways to represent a function, this representation would be what we call algebraic or analytic. Okay, you have a formula to represent the function, that is an algebraic representation. Okay, here is another function. What is it? The population of the world across various decades starting with 1900. So for each year for which the data is given here, there is a population, right? And every year that is given in the table has been matched. You have no blanks on the other side. So there is an output for every input, and the output is unique. Okay, so you don't have two different populations for the same year, right? So it is a function. And what kind of representation this is? This is a numeric representation or tabular representation. Okay, so in this kind of representation, basically you just list all input output pairs. You could have represented that as pairs like this, okay, like 1900 here and 1650 here. And continued with all other ordered pairs, okay. Here is another function and another way to represent the earthquake. Okay, the amount of the what you call the magnitude of the earthquake is measured like by this seismograph. It's a graphical way to represent. So what is the function of what here? The amount of whatever vertical ground acceleration is a function of time here. As time progresses, the acceleration is changing, right? And what you have, we have a graph to represent the function here. All right. So this will be a graphical representation, visual or graphical representation of a function. In functions, you will notice that in my slides here and there, I have highlighted some parts in green highlight or some other highlight color. That would be when it is important and I want you to special attention. Okay. And so one thing I wanted to say is like in how we can use different letters to write a function. Like the area function can be written as f of r, okay, a function of r. And sometimes we also write a equals a of r. So both are fine, okay. And depending on, again, your needs, you can do that. And here is in the second sentence, here is the definition that I talked about earlier. I might be moving quickly through the slides, right? The good thing is you can always pause the video and read through the slide, okay. The value of f at x is read as f of x and denoted like this, f of x, okay. And there are two things about a function. One is domain, which is the set of input values. One is range, the set of output values, okay. And when you write a function like a formula f of x equals something, that x there represents an input value. Which input? No particular input, an arbitrary input, okay. When you have a formula, we call that an independent variable, okay. The x is the independent variable, the input, and that input, the output of that input is processed by the function and it produces an output. That is your y, okay. Y equals f of x, and that is your dependent variable. Y is dependent, x is independent, okay. Here is another way to look at a function, which is very useful, especially later when we study function compositions, okay. When we combine two functions through composition, this point of view will be helpful, which is that of a machine, okay. You treat a function like a machine. So there is an input, let's say, and the function processes the input. You put in some raw vegetables and there is a food processor. It mixes them up, right? Slices them, chops them, and it produces the finished product, your salad. Okay, that is the output. So a machine perspective of looking at a function. So we talked about the domain earlier, right? Sometimes you will be given a function with a specified domain, like this we write f from. Okay, this colon will be read as from. A function f from 0, 1 to, let's say, 1, 2. Okay, so the input is the numbers between 0 and 1. The output is the numbers between 1 and 2. And you might then be given a formula, f of x equals x plus 1. So f of 0 will be 1, f of 1 will be 2, f of 0.5 will be 1.5. You just add 1. So the values come from here and they go into here, domain range, right? So the domain and range is specified here. Domain here, range here. But sometimes you are not given that. You are simply given a function. And I tell you that take the function f of x equals under root, let's say, x plus 2. Okay. Now the question becomes, what are the input values? Okay. And in such cases, many times we try to take the largest possible set of inputs. And that largest possible set of inputs, all possible inputs, when you put them together, that is called the natural domain of that function. So the term natural domain refers to the largest possible domain. And finding the domain and range of a function is an exercise in itself. Okay. Not getting into details, but quickly I'll tell you here. In this case, the domain of this function f, that is another way to write it. Okay, d of f, the domain of f, right, is all the numbers from negative infinity 2 to infinity. Why? Because there is an under root sign, right? So you cannot give anything less than negative 2, like negative 3. If you plug in negative 3, it becomes negative 3 plus 2, which is negative 1. And under root of negative 1 is not a real number, right? So you want to make sure that you choose your inputs in such a way that your output is defined. It exists as a real number. Okay. So in this case, for this function, the domain would be negative 2 to infinity. Okay. So by default, if nothing is mentioned, if no restriction is given to you like this, domain means natural domain. Okay. Here is another way to represent functions, the mapping diagram or arrow diagram. Okay, another name for it is mapping diagram. And what do we do in this diagram? We list, we draw one circle or one oval with domain elements, one oval with range elements, and you point the arrows. Okay, and useful, right, for small finite sets, definitely. And also you can represent infinite sets with the function by using dots after that. But there are other ways which are more useful for that. Okay. Good thing about this representation is it's very direct and immediate. Okay, you can look at the diagram and you can immediately decide the inputs and outputs, and you can also decide if it is a function or not. For example, this is a function, okay, which we are going to talk about in a second again. But anyway, what's the harm in talking now? If I had this a defined to this also, if there was one more arrow like that, then that would have been a red flag, like the red line there. Okay, that would be not a function. Not a function. Okay, if there was one more arrow. I'm going to erase that. But as such, what is given here is a function. Okay. Which brings me to yet another representation, the graphical representation. Right? We draw graphs to represent many functions. First, the definition. The definition of graph, analytic definition, okay, is it is the set of points x comma f of x. What does that mean? The input and the output, right, makes a point. And if you take all points like that and collect them, that's your graph. Okay. So, and we normally, in coordinate system, in the rectangular coordinate system, when we plot points, we write them as x comma y, x on the horizontal axis, y on the vertical axis. So that y is f of x. That is one of the reasons, why we write that equation, y equals f of x most of the times, because f of x, the output value of the function at a point, is the y coordinate. Okay. And what is the usefulness of the graph of the function? It gives you a behavior of the function, first of all. We talk about that later also, whether it is increasing or decreasing, where it is increasing, where it is decreasing, where does it have a max value, and where does it make a turn, right? It gives you a behavior of the function visually, and it gives you the history of the function, especially if it is a time dependent function. Okay, like the seismograph that we saw earlier, you can see, in the history, what happened in the past. The graph shows you that. Okay. Again, just to highlight the fact that the point on a graph, every point on a graph is x comma f of x. So that f of x is the y coordinate here. Okay. And x is the x coordinate, of course, the distance from 0 along the x-axis. Okay. And not just that, there is some more utility to graphs, which is it can give you the domain and range immediately. How? Suppose, I have this graph of a function, this part. I can look at all the x values and find that here, that's the domain. Then I can look at all the y values that it takes and find that, and that's my range. So by looking at the graph, I can identify the domain and range. Okay. Let us do one practice problem here. Take this function. You can pause the video, write your answers, and check with me. I recommend that. Okay. F of 1 is 3. I hope you are checking and you got this right. F of 5. Okay, 2, 3, 4, 5. 5 is not exact, it's approximate, so I'm going to write approximate. I don't know, it's below the x-axis, so it's a negative value, maybe negative 0.8, let's say. Okay. And domain and range. Okay, I'm writing D for domain. And you can see the extent. It goes from x-axis or y-axis here, which is at 0 to 5, 6, 7. So 0 to 7. And the range are the y values here to here. You have to write the smaller value first. Okay, the lower value is negative 2, and the upper value you can see 1, 2, 3, 4. Negative 2 to 4. Okay, by the way, the equation of those lines, we're reviewing, right? Why not review whatever comes up? Okay, the equation of those horizontal lines will be y equal to 4 and y equals negative 2. Okay. Representation of functions. We have already covered the idea, but let's formally mention it. Verbally is a description, like you can say, the force of gravity between two objects is some constant times the product of the masses of the objects divided by the radius square of the radius between them, like that. You can describe what the function is in words. Okay, that is verbally. Numerically is like table of values. The table is not literally a table, it could be ordered pairs, like that. You could just list them, or anyway. Okay, basically input and output are explicitly given, like the values are listed. That is numerical. Visually is the graphical, which also includes the arrow diagram also. Okay, the arrow diagram and graph. But arrow diagram can also be considered numerically if you think that it gives you the explicit values. It's really not a super fun, like strict science here. Okay, algebraically is explicit formula, and I said another word for algebraically is analytic. Okay, that is like y equals x square, the equation of a parabola. Okay, so the question becomes one important question whenever we deal with the functions is it a function in the first place? Because not every formula is a function. Okay, not every table of values may be a function. Remember at the beginning we said this definition, right? And I had highlighted, or I had filled in two words which are important: every and unique. So the every input elements must have a unique output. When that condition is satisfied, your relation or the formula is a function, otherwise not. So when we ask this question, which rules define functions, we are basically trying to apply this definition to whatever representation of function you have. If you have a graph, you have to apply this rule in the graph. If you have numerical representation, you have to apply this rule to that numerical representation. Okay, how do we do it? Let us see. If it is a graphical representation that you are given, we use the vertical line test, VLT in abbreviation, very important test. Okay, and very simple. You look at the graph, try to think of a vertical line anywhere. If that vertical line intersects at two different points, it's not a function. So simple. Okay, that means a vertical line should intersect at only one point on that graph. Let us see examples. On the left side, you see the shape of that function. You have this vertical line. Not only this, at this point, anywhere, even if you move that from left to right, at any point, it is only going to, at any position, it is only going to intersect at one point on the graph, right? It passes the vertical line test. It is a function. Whereas if you look at the right side, see, if I draw a vertical line here, it will pass that vertical line test there. That's not enough. Okay, because the domain is all the x values, right? And if you slide that vertical line to this position and some more positions around there, it is intersecting at 2 points, more than 1 point. It is not a function. It fails the vertical line test. Okay. Numerically, how would you do? If you are given a list of values or a table of values, you look for situation like this: A, B, and AC. What does that mean? That means, for example, if you are doing an arrow diagram, A would be here, B and C would be here. And it basically means A is mapped to B and A is also mapped to C. So those are, or, if you think of that in a graph, if A and B are like A, B, C are all numbers, okay, because the functions themselves are general concepts. Okay, you can find functions of fruits and vegetables. Okay, and their color. You can have a function in which fruits and vegetables are mapped onto their colors. There's no number there. You can use numbers to represent those fruits and vegetables and then make it a function of numbers, right? That is why we study mostly functions of numbers. But what I'm trying to say here is, suppose, let's assume that that has been done and we're dealing with numbers only. Then AB and AC would be like this. AB is here, AC is here. Because A is the same, right? The first coordinate, the X coordinate is the same. So it will fail the vertical line test. We don't know other points. We don't need to know other points. It fails the vertical line test. Okay. So you look for that. Now this is a tedious task analytically. Okay. So this kind of thing would be difficult to do if you are given in this form, So this maybe mapping diagram is better, I'll just map, and the moment you see two arrows originating from one point, you know it's not a function. Okay. Analytic. We looked at graphical, numerical. What would be an analytic way to know whether equation is a function or not? In analytic representation of a function, you are given an equation, right? Now, how do you know whether it's a function? One way is to convert to graphical. Take that equation and draw the graph. The graph of the curve with that equation will be this here. And now if you draw a vertical line, it intersects at 2 points, so it's not a function. Okay, that is one way. The other way will be you solve for it. Now, you want to know what is y, right? The y is the dependent variable, on the y-axis. So take that equation and you will get y square is equal to x plus 2 when you solve that equation. Okay. So when you find y, you know this, right? When you take square root, you get plus and minus. So you get two values, right? Y equals under root x plus 2 and y equals negative under root x plus 2. So for the same x, you get two different y's, y1 and y2, positive sign and negative sign. Hence, it is not a function. And that's the discussion here. Okay. But then you can do some work to make or extract the functions out of such graphs which are not functions. Okay. For example, in this case, you could look at the upper half separately and lower half separately, and each of them is a function. Okay. I'll leave it at that idea. I'll not explore more. Another type of functions. Okay. Now we're looking at some classes. One idea is piecewise defined functions. And this is important idea because so far all the graphs you have seen, there is one single piece of smooth graph, and when it passes the vertical line test, you have a function, right? But that's not always the case. You can have functions which look like different graphs stitched together. Okay, and that is exactly the idea of a piecewise defined function. For example, okay, you could have something like this, here like this, here like that. And continuing here like that, and so on. Okay, let us look at some examples. Say a function is given like that, f of x equals 1 minus x and x square. For x less than minus 1, there is a different rule. For x greater than minus 1, there is a different rule, right? So how would this work out? If I want to evaluate f of minus 2, that is less than minus 1, right? I'm in this territory. Okay, so I have to use this first rule. And that f of minus 2 there would be 1 minus minus 2, which is 3. At minus 1, I'm still in the first rule because x is equal or less than minus 1, right? So 1 minus minus 1, 2. But when I am at 0, 0 is greater than -1. So now I'm in the second row. That will be 0 square equals 0. So you use two different formulas, but it is the same function. That is the super important thing here. Okay, it's one function, but with different rules. Okay. And here is the graph. You can see on this side, that's 1 minus x. And on this side, that is x squared. All right. And they don't meet. So there looks like, two different pieces here. And this is important. Okay. This is the idea of continuity, right? Another concept in functions. The function is not continuous at this point. That's what we say. Okay. Not continuous at x equals -1. Okay. A very important example of piecewise functions is the absolute value function. Okay. What is the goal of the absolute value function? You want your output to be always positive. No matter what input you give, the output should be positive, right? That is the absolute value function. Why is it a piecewise function? Because you can define it like this. Okay. And what is the definition? If the number is already positive, so I'm including 0 with positive. Okay. Strictly speaking, you say non-negative. If the number is non-negative, you leave it because it is already non-negative. But if the number is negative, like x is less than 0, you slap another minus in front of it, another negative sign. So negative of negative becomes positive, right? So the end result is always positive. And now you have two different rules in two different parts of the domain. It's a piecewise function. Graph looks like this. On the right side, you have the line y equals x. On the left side, you have the line y equals negative x. Okay. And in this case, unlike the previous function, they meet at the point 0. So it is continuous. Even though the rules change at 0, the function is still continuous at 0 because the two parts of the graph meet there. Okay. Another example of piecewise functions is the step functions. Okay. What is a step function? This has many practical applications. Okay. First, I will define what it is and I'll talk about an example. In a step function, your domain is divided into subintervals. Okay. And that is done in any piecewise function. In those subintervals, the value is constant. Like between 0 and 1, the value of function is 1. Between 1 and 2, it is 1.15 and so on. Okay. Such a function is called a stepwise function, step function. What is an example? The money, the charge the post office makes for your parcel, depending on the weight and size of the parcel, right? Let's say, you take the same standard size and you're now, for different weight categories, there is a different amount of money they charge, right, for shipping the parcel. That's an example of a piecewise function. So a graph looks like this. Hence, it is called step function. Between 0 and 1, it has this constant value. Between 1 and 2, it has this constant value and so on. Okay. That is step function. Okay. Now I'm talking about a related concept about functions here, not the step functions. We're done with that. Okay. I want to draw your attention to something else. You focus here and you see there is an open dot circle there and a closed circle there, right? In sketching the graphs or interpreting the graphs, that is very important. Okay. The closed or filled circle here means that is the value of the function for that particular x, like f of 3. F of 3 here is this value. Okay. Whereas that open circle there means that's not the value of the function at 3. But after 3, for x greater than 3, that rule applies. Okay. So open is used when that is not the value of the function. Okay. And it comes generally with what we call the open intervals, or the open side of an interval. If one side is open, the other side is closed, like in these cases. Okay. And you can check this by going back to the previous page and looking at the definition. What was the definition? See, between 3 and 4. So 3 is less than w less than 4, right? So that rule was not applicable at 3. That was applicable to values greater than 3, but equal or less than 4. Okay. That's a quick review on that topic. Moving on. The idea of even and odd functions. Okay. Very simple idea. Functions that have a symmetry, okay, we'll talk about that, similar to x square are even functions. If they are similar to x cube, they are odd functions, basically odd powers and even powers. Okay. But what do we mean by some properties similar to this? Here, if you evaluate f of negative x, for the function f of x equals x square, you take negative x and whole square it, you get the same output, right? When you square, the negative sign goes away. So f of negative x is the same as f of x. And that will happen for every even power of x, right? So these kind of functions are called even functions. And here is a graphical view of that. At negative x, the y value is the same as what you have at positive x. Okay, now think about this. This is not going to happen at only one point. Or it's not enough if it happens at only one point. It should be true for every point. For every x and negative x, the y value should be exactly the same. Now, what does that mean? That means if you draw a line through the y-axis, or just look at the y-axis, on the two sides, the graph should be identical, right? That's what we call symmetry. The graph is symmetric with respect to y-axis. And that becomes the characteristic of even functions. Okay. What about odd functions? Similarly, for odd functions, they behave like the odd powers of x. So if you evaluate f of negative x, that will be negative x cubed. Now, negative 1 times negative 1 times negative 1 will be negative, right? So you get negative of x cubed, which is negative of f of x. So if you evaluate a function at a negative x value, the output also is negative of your original output. Which means, let's do it here, okay? If at x here, the value was here, at okay, let me try to be more precise. At negative x here, the value will be here. This output is f of x here. Here you will get negative f of x. Okay. And that will happen not only for one point, for every single point, right? So which means if let's say my graph here was like that, then its counterpart, I would say, here should be like that. Okay. That's an odd function. And what do we notice? Now it's not a line, but if you take any one point here, its counterpart is a point there. And how do we get to that point? Start from here and go to the origin and continue your journey. Go an equal distance on the other side and you'll find your counterpart. Okay. We call it symmetric with respect to the origin. Okay. That's an odd function. That symmetry is coming on the next slide also. Let me emphasize this analytic part here. Okay, f of negative x is negative of f of x. And here's what I was talking about, the symmetry. Okay, it is symmetric with respect to origin, and you need to understand the meaning. If you want to find the counterpart of a point, start from here and go to the origin and continue on the other direction, same angle, same straight line, go an equal distance, and you will find your image there. Okay. At the bottom of this page, I have circled and highlighted another important concept about odd functions. It looks like, you could obtain, if you know the right side of the origin, you could rotate the graph 180 degree and get the left side and vice versa. Okay. That is also a way of understanding what symmetric with respect to origin means. It's like origin is like your pivot point, like the fulcrum of a seesaw, right? About which you can rotate. And if you rotate 180 degree, you get the graph on the other side. Okay, here are some examples and important conceptual clarity on the concept of odd and even functions. We'll discuss all three here. We don't need to look at the solution. We will discuss them. Okay. So the idea is this. The first one here is combination of both odd and odd, right? So the overall function is odd. Okay. Here that is even, and you need to concept. Constant function also is an even function. Why? Remember, x to the 0 is 1. Okay. Except 0 to the 0, every other, x to the 0 is 1. So 0 is an even number. So it's an even power. It's an even function. And the result also is an even function. Okay. Whereas here, x is odd, x to the 1, right? X squared is even. And the combination is neither. Okay. So a lot of things are happening here. Let me repeat. Add or subtract odd functions, you get odd. Add or subtract even functions, you get even. If you add or subtract one odd and one even, you get neither odd nor even. Okay, neither odd nor even. So, which also means another thing. Not every function is either odd or even. Okay, you can have a function which is not symmetric with respect to y-axis, right? Not like a mirror image, and also not symmetric with respect to origin. It has some different behavior on this side and some totally different behavior on the other side, and no connection, right? So not all functions have to be odd or even. Okay, keep that in mind. Another concept I wanted to highlight here is the number 2. Okay, the coefficient is 2, so don't think that's going to be an even function. Okay, the odd or even is about the exponents. What is the power of x? You look at that, not the coefficient of x. Okay, if that was 3 there, or 2 there, doesn't matter. It's an odd function because it's x to the 1. Okay. Here are the graphs of typical, odd functions. This is the graph of x cubed, and this should be the graph of some negative x to the power 4 plus 1 maybe. Okay. Oh yeah, sorry. We talked about that here. Yes, x1 minus x to the power 4. Oh, x to the 5 plus x, it seems. Okay, not x cubed. X cubed will have a similar graph. Okay. And the last one is here, which is neither odd nor even. And how do you know that? Now, if you look at y-axis, the two sides are not mirror images. If you try to look through origin, what about this point here? If it was an odd function, its counterpart should have been here, right? Which is not there. So it's neither odd nor even. You can try to determine that. graphically also. Okay. Another concept, increasing. Oh, before we go there, just 1 second. I will briefly, talk about these two trigonometric functions. You don't need to study trigonometric functions in detail if you don't require in your course. If you don't know them, don't worry. I'm only talking about one idea about odd and even functions, okay, which you will understand. So it turns out in trigonometry, sine of minus x is minus sine of x, and cos of minus x is cos x. Okay. So if you go by that analytic definition that we wrote earlier, this is even and that is odd, right? Here, okay, we're talking about this. So what I wanted to say is the odd and even is not only about powers of x. Okay. We're not only always talking about polynomials. There could be other functions like sine and cos, trigonometric functions, which also have the odd or even behavior. Okay. So the odd and even functions is a property, not only a property similar to the odd powers and similar to the even powers. Those are used as references. We're not saying those are the only odds and even functions. Okay. All right. Increasing and decreasing functions. So basically, in which parts of a graph a function is increasing and where it is decreasing. That is the idea. That you can visually see it's increasing here, it's decreasing, and then it's increasing, right? You'll tell me that's not much fun to study. What we are interested in is this increasing and decreasing gives you some important points on a function which are called max values and mean values. Okay. And in real world applications, that is a crucial idea. Like a simple example, if you are running a business and you, let's say, you have various, not business, manufacturing unit, some factory, let's say, and you could, produce different goods of different qualities or different variations, if it is a furniture factory, tables and chairs, right? How many tables, how many chairs, and there will be functions that you can use to model the profit that you make out of it. So you might be interested what you should do so that you get max profit. Just to give an example, in the same way, there are any number of situations you can imagine whether you want to either find the max or a mean. Okay. So this increasing and decreasing helps us in that. How? If you look from A to B, the function is increasing, and then from B to C, it is decreasing. So what happened exactly at B? It must have reached some kind of max value, especially because it is continuous. Now, I'm not getting too much into detail. Okay, just keep in mind that the graph is continuous there, and which means we are able to draw it freehand. And then I can guarantee that B must be the max because it was increasing and then it is decreasing, right? We call that kind of max as a local max. Okay. Now, you'll ask me why it is local max. Because locally, if you look at around here, that is max. Okay. I'll come to that again in a second. Let me talk about the point C. That is a local min. It is minimum in that neighborhood, Okay. So if you know the intervals where it is increasing and the intervals where it's decreasing. So the word if you read the paragraphs written here, it talks about intervals, right? And the domain of a function can be divided into intervals. And in those intervals, the function would be increasing or decreasing. All right. And if you have the graph, you can talk about max and min. I said local max, local min. But what is absolute max? Absolute max is in the whole graph. Right? In the entire graph, B is max. Right? B will be absolute max. In the entire graph, Okay, by the way, local max and local min, I need to add some more. D is a local max because there is no right side. If you look at left side, D is max, and similarly, A is a local min. Min means minimum, okay, local minimum here. Because, if you look at its neighborhood, that's the lowest point. Now, what is absolute max? In the whole graph, B is max. In the whole graph, A is minimum. Okay. The point is, not every local max is absolute max, right? There's only going to be one value of absolute max. You may have more than one point where the maximum takes place, but there is only one value of absolute max, only one value of absolute min. But you can have many more local max and local mins. Okay, that is the idea I wanted to discuss here. There is an analytic aspect to this, which also you should be familiar with, because you may not always be given a graph, right? Analytically, how will you know if a function is increasing on an interval? And here is the definition, the one that I have highlighted in green color. If a function is increasing, what should happen? Whenever you take 2 points x1 and x2, where x1 is less than x2, then the corresponding f of x1 should be less than f of x2. What that basically means is, in the graph, if this is x1 and this is x2, x1 is less than x2, right? x1 is on the left side of x2. Then on the graph, it must be the case that f of x1 is here and f of x2 is here. And that should happen for any two x1, x2. Okay, then you would say the graph is increasing from here to here. Obvious, right? But we're just articulating it. The important thing is every pair, which even in the printed slides, that is in italics. Okay, because that is important. For every pair, this should happen. Whenever you take left and right point, the function value on the left should be smaller. Then you say the function is increasing on that interval, on I. That is important. Okay, on that interval I. Okay. One last idea which was not covered in these slides provided by Singh is concavity. Okay. Also an important idea about functions. Just like the increasing and decreasing behavior, you can look at the face of the function. Like we say that this is facing down. Okay. And obviously this side is facing up. That is called concavity, and we call the facing down is called concave down. Okay. And here you have concave up. And it changes at this point. And that is called an inflection point. These terminologies you want to be familiar with: concave down, concave up, and where the change takes place, that is an inflection point. That is also a property of functions. I'll give you an example where it is makes sense, okay, to look at this. When it is concave down, you see the growth is getting slowed down. Okay. So this could be something like, a disease when it is spreading in a community. It might be growing rapidly, but gradually, it starts to flatten, right? More and more people are infected, but the rate is decreasing. Okay, and gradually, at some point, it hits a peak, and then number of infected people starts dropping, right? So you would know that is happening if it is concave down. If you are an analyst and you are looking at the public health data and you want to know if the trend of the disease is decreasing, so you will not just count how many people are infected. That will be misleading. You have to say, because in this region they're increasing, more people are getting infected, but the rate is decreasing in the long term because it is facing down. Okay, so that is one example, a real world example. I will pause this video on here. In the next slide, I will talk about some important types of functions. Okay, we talked about functions in general in this video. We will next need to study the some basic categories of functions which are used in real world models and also in mathematical studies. Okay, see you there. Thank you for watching.